before I go on to the presentation itself, few disclaimers or few common understandings. Like, this is whatever I'm going to talk about. It is in my personal capacity. Not It has nothing to do with my organization. So you can blame me, not my organization, if anything's wrong. Uh, Secondly,
Akhilesh, put your
sir,
presentation on. Yeah. 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 You got it. Make it full screen. Yeah.
good. So I was telling when I was interrupted that the subject is such that it will involve a lot of references to standards, specifications, and manuals. Unfortunately, I couldn't have done without that. And you will also see a lot of data and parameters related with the subject. So, with these things in background, let me begin the session for the subject: signaling and rolling stock compatibility. Now, signaling generally is associated or interfaced with many subsystems, and this talk mainly focuses on interface between signaling and rolling stock. So this will be kind of structure of the presentation. I'll briefly describe what I mean by compatibility. What are the rolling stock parameters that can impact on signaling, primarily impact on trend detection, other components of signaling, and interlocking design. EMC is one of the most complex subject, which requires a session in itself. But I will try to introduce that and try to refer to relevant specifications and standards that will point you to go to if you want to seek more information. And as I said, this presentation will be replete with standards that are used in this compatibility assessments. Some of the IR processes for compatibility, generally through RDSO assessment and approval for new vehicles, and also some improvements and suggestions. I will give some time after changing the slide, because I know there will be some delay at times in the slide appearing on your side. So starting with what is compatibility. So as it is written there, capability of a system to work in an orderly and efficient manner and integrate with other subsystems without any modification or conversion. And signaling is one technology or one topic which interfaces with almost every other subsystem in railways, be it track, rolling stock, operations, traction, telecom. Here we are focusing on signaling and rolling stock compatibility. So this compatibility, ensuring the compatibility between these two is possible when we have identified, defined, and shared all the relevant parameters and limits with all stakeholders, so that they can take care in their own subsystem designs. So some fundamental requirements between these two subsystems are that all vehicles shall always be detected. That means if there is any new vehicle being introduced, it must be able to be detected by existing trend detection systems. So that means the responsibility for compliance or compatibility lies on the new vehicle. And if there is a new train detection system is being introduced, then it must be compatible with existing. Thank you, sir. I think this is good. So any new vehicle, any new train detection system, it must be compatible with all the existing vehicles. So responsibility lies on train detection. So this is the philosophy. There should not be any mutual interference beyond acceptable limits, and these limits you will see are defined for the vehicles and for the train detection systems. But as you know, the vehicles generally they deal with the kilowatt or kilovolts and kiloamperes, whereas train detection deals with millivolt and milliamperes. So most of the time, the it is signaling system or train detection system or ATP system that is susceptible for interference from this high energy rolling stock components than other way around. Though the responsibility and standards, they talk about both emissions and immunity from both sides. So there are limits for both of them. Uh, Agreed operating parameters, because trains work on signaling provided by the railways, and basis of all the signaling depends on a lot of train parameters like braking distances, shunting capability of wheel and axle thing, and maximum traction current, maximum wheelbase. There'll be a lot of things, a lot of parameters you will see during the course of this discussion. So these are the fundamental requirements. So this presentation, we will together explore what are the rolling stock characteristics that have an impact on signaling system design and performance. Characteristics like physical, braking, and electromagnetic. I have used schedule of dimensions for Indian Railways very intensively because a lot of things are referred, especially the physical characteristics. They come from schedule of dimensions. Some cases, international practices will be highlighted, especially the UK railways. And that's obvious because of my association with that system for 4 years when I was on secondment or deputation with Atkins at Sharjah, along with some of other of my colleagues from Indian Railways. International standards will be quoted in not certain, I will say many of the cases also. So let's explore the first parameters and the physical characteristics of rolling stock and how they influence the signaling systems and components and design and performance. Maximum distance between two consecutive axles. Now this has a bearing on the fail-safe detection by track circuit or axle counters. Any of the train detection system, the minimum length of a track section is influenced by this parameter. If you have a track section length less than this maximum wheelbase, then of course you can see that the rolling stock could be standing there with one axle on either side of the track section, and track section not getting influenced or occupied, so to say. So this will not be in the right side, and then this is not desirable. So the maximum wheelbase is something which influence directly the minimum track section length. And if you look at our SOD provision for this, the maximum distance apart between two adjacent axles is 12.3 odd meters. That means a track section can never be less than this specified axle distance parameter. But is this enough to define minimum length of track section? Because even if you have, say, 13 meter of track section, you will still have some part of this vehicle overhanging beyond the track section boundaries. So that brings to the second parameter, the maximum length of a vehicle body. And this should be the minimum track section length. So that, when a vehicle is standing completely within a track section, its body parts do not infringe onto the adjacent track section on the same track. And minimum track section length should be depending on this parameter. An LHB coach is around 24 meters. So the minimum track section length should be a little more than this. And rightly so, the signal engineering manual specified the minimum length as
Akhil, sorry to interrupt you. Some block has come actually. Is it on your screen? We are also seeing on the diagram one square block actually.
no, nothing is there. Let me just.
Nothing is there. What about the other participants? Any blockages there on the?
Yes, yeah, there are three blocks.
Yeah. Now it has been cleared. Yeah, it has been cleared.
Block is coming, sir. Yeah. Now it is clear, sir.
Now it's clear. Yeah, please go ahead, Akhil. I'm sorry.
Okay.
Yeah, fine. It's fine. Yeah.
Thank you for that. So you keep telling me if any issue with
sure.
because
My job is that only now.
yeah. So the two rail length that is 26 meter is the minimum track section length defined in a CM, and that covers both these parameters from rolling stock. So we are good on that front. Vehicle overhang. This is I also discussed in previous slides that this is the vehicle body which protrudes beyond the last axles, and this is a very critical parameter when you are looking at clearance points or fouling points on a converging or diverging junctions. And this is the parameter which defines how far away from the fouling.
Again, blocks are there.
Okay.
I think is it because some people are doing annotation?
No, whenever some chat comes, it is coming.
Whenever chat is coming, now it has gone again. Let me check up. So anyone can.
There was one pop-up which I've clicked. Don't show me again. Maybe it will not happen again. But please tell me if it happens.
Yeah. Please carry on.
So the overhang I was talking about, a track section boundary, that means has to be defined. The overhang, at least minimum overhang away from the fouling point, so that even if a vehicle is standing or with the last axle just near to the track section joint, the overhang still doesn't infringe the other track. And for this purpose, this margin has to be defined on how far away from fouling point we have to keep the track section limits or insulation joint, or for axle counter, how far away that the sensor should be there. In this case, if you look at IR signal engineering manual and the track circuit termination, it says the distance between track circuit termination and fouling mark shall not be less than 3 meters. But I found one LHB coach design where I can see the overhang to be around 3.3 meter. So clearly there is some issue here. Maybe exchange of parameters here has not happened in the right manner. Either signal engineering manual need to be updated, because that's the easier thing to do than changing these rolling stock. But whenever new rolling stock design comes, it is for the signal engineers to check and ensure that this overhang is not infringing with the given provisions of signal engineering manual. Wheel shape and size, and this is very important for fail-safe detection by axle counting systems, because they work on the electromagnetic field of the sensor being disturbed by or influenced by the wheel, and most importantly its flange. So wheel diameter and the flange dimensions, these are the key parameters that influence the axle counter working. And we have some understanding on this aspect, that whatever axle counters are approved on Indian Railways, they cannot detect a wheel less than 700 millimeter. In fact, unfortunately, I've written M. That is a wrong value. 700 millimeter in a safe manner. So any rolling stock wheel has to be above 700 meters, and most of vehicles are plying on Indian Railways, they are good in this respect. The minimum and maximum diameters are 914 and around 1 meter. So we are good on that. Wheel flange profile and limits on their wear, because wheel flange is the part which is influencing the magnetic field of the sensor of an axle counter in most impactful manner. So this is most important, that the wheel flange width and height is specified in IRSOD. They are always complied, and it is also on the axle counter suppliers, alternate detection suppliers to ensure that these dimensions of the wheel flange and diameter, they are compatible with the wheel sensing limits of their sensor. So these are the dimensions which is specified, and most of the axle counters, they respect these flange dimensions. Another aspect, of course, with the flange dimension is the safe traversal of the wheel over the crossings and points and crossings. So if you don't have these flange dimensions correctly, it can have an issue on that front. But of course, that's a separate issue. Axle to axle distance. Now here you will see there is something written as EN 50617-2. This is Senelec standard for axle counters and their safe operation. And this also captures some of the interface issues, not just with the rolling stock, but also with traction and things like that. So it's quite an important specification with respect to axle counter and its fail-safe working. The key requirement why axle to axle distance matters for axle counter is that with the given speed, the given maximum speed, the second axle will come, how soon it will come onto the sensor, and the sensor sensitivity should be good enough to distinguish between those two sensors in that given time. So if you have wheels coming so rapidly that sensor is still processing the first axle and the second one has come, it will have errors. Of course, this will be on a safe side kind of error, but still this will result into an unreliable working of axle counters. So that is why this is an important parameters. And for the of course, this 50617 being an European kind of standard. So in this, they have assessed all the European axle counting systems, some 10 to 15 systems of all the suppliers, all the axle counters present in Europe. And they have identified the worst case scenario or response times. And the requirement is that the two axles should be 25.9 millisecond away from each other at given maximum speed. And if you look at, if we assume 200 kmph, this 25.9 millisecond gives around 1619 millimeter of axle to axle distance. And this should be the minimum for any given vehicle. And in Indian Railway Schedule of Dimensions, the minimum rigid wheelbase for a bogie truck of any vehicle is specified as 1830 mm generally, and for passenger vehicles it is 244 mm. So we are good on that respect, even if we are running at 200 kmph, though none of the trains we are running presently at that speed. So that means if you make it 140 or 150, the distance, minimum distance will be still less, and we will have much more margin here. So we are good in this respect. But the important thing here is that we have to take care of this issue whenever a new vehicle is being approved. This is one thing which need to be seen by signaling engineers while approving new vehicle. Another physical parameter or characteristics of rolling stock which impacts train detection and especially the axle counting systems is the sinusoidal sway of train, or what you call play. Because if your flange goes so far away from the rail that it is beyond the detection range of the wheel sensor, then you will have issues of not getting detected, or it will cause failure because anyway there is some influence. And this sway is defined, the maximum sway should be 50 millimeter, I think this parameter. Yeah, so A sin, this should be 60 millimeter maximum. So that means the distance from this rail head, the inner edge of the rail head, to the inner edge of wheel flange of any wheel when it is passing over a wheel sensor, it should not be more than 60 mm. And if I calculate with the given schedule of dimensions on Indian Railways, maximum sway, which comes to around 50 mm. So we are good on that front because 50 mm is less than the specified sway. But again, a little caveat here that this 60 mm parameter is based on the axle counting sensors used in Europe. And so on that respect, on their influence shown, it is arrived at. There are some systems which are developed here locally. So for that, maybe we have to identify this parameter, how much it should be. But otherwise, from this perspective, our sway is good for fail-safe detection by axle counting systems. Wheel metallurgy. because we all know that track circuits, they work on uh, successful shunting by any axle and wheel combination. So the metallurgy will have the impact for sure. If we have the combination of metals which oxidize, oxidation takes much more rapidly, then we will have the wheels getting rusted much faster, and we'll have poor shunting kind of issues. You will also see that the tread of wheel can also get contaminated by brake residue, and this may interfere with the shunting. So here also again metallurgy comes in picture, metallurgy between the brake shoe and the wheel itself, and how much brake residue actually is getting formed and getting stuck to the wheel itself. Another thing which you have to see from signaling perspective, the key requirement is the contact resistance between individual wheel and axle combined, and that should generally be around 1 milliohm for fail-safe working of track circuits. Though our shunt resistance is 0.5 ohm, but the wheel and axle combined should not give more than this resistance, because in this you'll also have to add the contact resistance between the wheel and rail itself, and then that becomes the shunting resistance. So this is one parameter, 1 milliohm, which I've not come across on Indian railway standards, but I've come across on UK railway documents. So because the technology is same for the shunting, and there also they use 0.5 ohm shunt, so that's why it could be an important aspect even for us to realize and know. Some of these things which we generally don't look at, but they can also have an impact on the signaling system, especially trend detection systems. So things like vehicle weight, which if now you look at that, weight is something which determines the contact resistance between wheel and rail itself. Also, the disc and tread brakes. Sorry, the tread brakes, they generally tend to have kind of abrasion on the wheel surface and keep it clean. So they provide very good shunting for the track circuits. Whereas if you have disc brakes which are not on the wheel rolling surface, then the lack of abrasion on the wheel surface would degrade the electrical performance of the wheel interface. And so this comes from actually from introduction of a new new generation of vehicles on one of the railways. I think it is UK Railway, where the new vehicles, when they were being run, they were causing a lot of failures, and some of them were not getting even detected, and some of them were shunting intermittently. So these issues were investigated by a consulting firm, and they came up with these results that in this new generation of vehicle, these two changes happened. One was the brake was disc type instead of tread, and that was causing lack of abrasion and giving ineffective shunting for the track circuits. Another interesting factor appeared to be that since this new generation vehicle has very good improved suspension in the bogies, so instead of kind of bouncing, scrapping, and siding around the track, along the track, the wheel on these new bogie was running straight and true along the rails. So with a significantly reduced scrubbing action between wheel and rail. So and this was causing again the shunting issues, track section not being shunted. So then they came up with wherever they have these kind of improved vehicles, and especially there since many of these vehicles are self-propelled train sets instead of having locomotives and other kind of things. Number of axles or wheels, number of axles were also limited because of smaller train consists. So these kind of issues became very significant there. And they came up with a new technology of which will be installed on the both track side and also on board for track circuit shunting. And then came this track circuit interference actuation devices, and they will aid in track section shunting. So this was about physical characteristics of the rolling stock, which impact on signaling systems, mostly train detection systems, because they are installed on the track to detect the trains and vehicles. We come to the second part now, and here we will look at the braking characteristics. So braking is the key factor in signaling design. All trains, of course, they must be compatible with the inter-signal distance or the braking distance provided by the signaling system. So that means when we design signaling, we should know the worst case braking of the trains at given speed, and that should be the deciding factor on where we place the signals, especially the warning signal. The warning signal means the signal which tells that you're going to encounter a red aspect or a stop signal ahead. And that's the signal in case of 4-aspect territory is double LO, and 3-aspect territory it is LO. So that means in 4-aspect territory, you should have sufficient braking distance for any train running at that specified speed in that section to stop between double LO to red, and stop by using full service braking, not emergency braking, because system is designed for normal operations, not emergency. And there are some issues on this side for having full service braking distance available for each of the sections at the given speeds. Unless we have that, we cannot customize this design for individual sections. So on Indian Railways, we generally use this concept of having a distance signal at 1 kilometer. That means the train running at the maximum permissible speed in that section should have a braking capability of braking in 1000 meters. Possible ways in which these braking distances can be determined is by theoretical assessment of the braking rate based on Newton's laws of motion. and the distance traveled during braking from any given initial speed. So this is theoretical assessment. And secondly, to confirm those theoretical assessment and validity of those results, series of physical trials can be conducted with actual trains with varying loads and speed on this railway system. And if you have validated result given for a train,
వాళ్ళు ఆల్రెడీ మెయిల్ ఐడి ఇస్తారు సార్ ఒకటి, దాంట్లో మనం రిజిస్ట్రేషన్ అయితే ఒక ఐడి ఇస్తారు సార్. ఐడి
Sorry, I think somebody has interrupted, so I muted them all. Okay, you can go ahead. Sorry, okay, carry on. Akhil, your voice is not coming. Just hold on. Check up your mic.
Yeah.
Yeah.
Sorry, I forgot that you have muted everyone.
Yeah. Okay, it's fine. It's fine.
Yeah. So I was discussing that if we have braking distance available, validated for a specific train consist at a given speed, then we can extrapolate the results for different gradients and different speeds. So since signaling design has to consider the worst case scenario, that means the braking distance, whatever we are taking, should include the circumstances like poor weather conditions, like it's raining, so the track will be a little bit slippery, so braking distances will be larger. Driver's reaction time to a warning, driver's misadjustment of brake application or mistaken judgment, system reaction time. So when you apply the brake buildup and progression of this brake application along the train, and all these factors, they impact on the overall braking distance for a specific train consists. This cannot be done for one train and taken for all the trains. So unless you have done some analysis theoretically for all type of train consist. And these results, then we should have somewhere available in a tabular or graphical manners for signaling designers to take care to customize the signaling for a specific section. But in absence of that, we have accumulated from our own experience these empirical distances, braking distances, and based on that, the signaling design is being done, and that may not be very efficient for all the sections because it is not customized based on braking distances of trains and the sections they're running on. And of course, these distances must incorporate safety margin because of these stated conditions above. So these are the, you will see there are some curves and tables in the slide. And this is what is available in UK Railways based on their theoretical calculations and trials and empirical adjustments at various gradients. They have come out with the speed and the braking distance chart. So at various gradients. So if you see that middle, a dark vertical line, so that is the level gradient, and left side is rising and right side is falling gradient. And smaller numbers written on these graphs are actually they are the train speeds. and I think this is given in miles per hour, whereas the braking distance is given in meters here. For example, how to read this, if we're designing a signaling in a section with an average gradient of falling gradient of 1 in 200, and where the maximum permissible speed for train is 65 kmph, and we go here, and the braking distance, which comes around 800 meters. So the distance from the warning signal to the stop signal should be 800 meters. So this is the way you can customize the design of signaling system for specific trains and the track systems. Same information which is in the graphs on the right is also given in the tabular form on the left, and for easy reference of signal designers, just to remove any confusion in reading the graphs. But this is something which is available in UK Railway, and I've also seen in many other railways. Whereas we don't have specific graphs for Indian railways. We can see, as we have seen, this comes from a practice on Indian railways of having 1,000 meter braking distance on a single distant area and 2,000 meter double distant or four aspect territories. So in our case, we have fixed, and this is easy for signaling engineers and for the design team, for project teams to execute and not vary the distances based on the gradients and the speed of trains running in the section. If you want to get a braking distance, of course, RDSO has a rolling stock directorate where they have the simulation tool. They also have the brake lab where they've simulated a lot of cylinders of a goods train and passenger train, and they can arrive at these braking distances in a theoretical manner. But if you take these parameters from RDSO directorate, then you will also see that they will always ask to undertake the actual field trials to validate this. And some of these things which are validated, they're also available with them. But generally, this table on the right, which you can see, this is for rolling stock, which is specified as one WFH7 loco with desired air brake coach configuration of AC3 tires. The various coaches are mentioned. Leftmost column has the speed, and then you get the braking distances for various train consists. And yeah, this is the full service braking distance. And so if we have this available for each kind of train which will be running, which is a mammoth task, of course, in itself, then the signaling design can be customized. Okay, so this was just to kind of compare how it is being done elsewhere and what is our approach to braking distance parameters in signaling design. This is obvious, of course. If you have trains which have better brakings, they can run at high speeds, like in UK, where the normal trains which run at 150 or 160, the Pendelano trains, they run at 200 kmph on the same track, same signaling. This is because they can stop at higher speeds. They can stop between the given braking distance when running at 200 kmph, whereas the normal trains, they can maximum run at 160 kmph to stop in the same braking distance. So Of course, the other requirements of track structure, signal sighting, and requirement of an ATP system on board, they are separate. I'm not deliberating on that. But key point which I wanted to kind of mention here is that braking plays an important role in running trains at higher speed and on the same signaling design. Alternatively, the signaling design has a very basic parameter, the braking distance, in its core. If any of you have worked on metro kind of systems, you will see this. The braking is the basic thing on which whole ATP design of CBT system or ATP systems of metro signaling design is based on. And some things which are specified by rolling stock suppliers is guaranteed emergency braking rate, the emergency braking build-up time, traction cutoff delay, and these things are taken by signaling design engineers to configure the ATP system accordingly, and they can influence your inter-train spacing in a moving block. So this is a braking curve or a braking model, which is actually described in one of the Cbtc standards mentioned here. And you can see that it takes care of all the suspected delay times. So like ATP reaction time, every system has a reaction time when you trigger it and when it actually outputs. Similarly, time to disable the propulsion, additional time to apply the emergency brake, and all those other things. And then based on this, the second train behind, it calculates its own safe braking model to keep a safe distance apart from the train ahead. Good. So that brings me to second part of the discussion, and this is physical parameters or physical characteristics. And now second part was the braking characteristics of rolling stock and how it influences signaling design. And third and last part is electromagnetic compatibility. So we have a lot of active semiconductor devices these days on our trains, rolling stock, that's locomotives, and they use the chopping or the the mechanism to use the power 25 kV AC or any other voltage in different tractions to convert that into the kinetic energy or motion. And then while doing that, these devices they kind of emit a lot of harmonics running up to very high frequencies, and the amplitude of those harmonic currents can actually come and influence some of the signaling components, especially on the track, because we know that on the track we have track circuits, AFTCs, sensors, wheel sensors. They all work on a given voltage and current levels in a defined frequency band. And if the rolling stock can emit or conduct that kind of energy into the rails, and that can become an issue with the train detection systems. So that's why this EMC is a very complex requirement, and it becomes more complex when you look at the variety of trains and variety of train detection systems available across the world. So the electromagnetic compatibility for a device, it is its ability of a device, unit of equipment or system to provide immunity in its electromagnetic environment. So we have this electromagnetic environment of traction, rolling stock, and emissions, without producing intolerable emissions. So both the two things, immunity and emission, are important. So, for example, a wheel sensor, it should not get influenced by specified limits of interferences from rolling stock. At the same time, it should not also emit any energy which can impact systems on the rolling stock, which looks generally difficult to happen because of different voltage and current levels of two systems. It is always that the signaling systems which get influenced, as I told previously, because the kilovolts and kiloamps of energy used by rolling stock, whereas signaling devices work on milliamps and millivolts. And we see that the signaling systems are more and more going into microprocessors, and data communications, and other sensitive electronics. And they can be affected by interference from external world, including rolling stock. Generally, the systems susceptible to these kind of interferences are train detection systems, radio systems on generally on metros, on Cbtcs, and onboard ATP equipment, even on a track circuit based ATP. Generally, there are three mechanisms of coupling the interfering energy with the victim. Or so in this diagram, if you see, there is a source. Let us assume this rolling stock, and which has a lot of semiconductor devices, which is converting 24 5-volt kVAC energy for using into propulsion system, and then it generates interferences by conductive or inductive and radiative manner, which can go to the victim component, let's say an axle counting sensor, and get influenced by this extraneous energy. And it is not necessarily that when this energy comes, the device will go into unsafe side, but most of the time what happens, the component or equipment failures, they increase when there is not compatibility between the two systems. So this is just to give a picture of railway environment, electromagnetic environment, on especially on electrified railways. So you have HV traction system, substations converting high voltage into 25 kVAC and distributing it along using an overhead equipment installation or catenary system, which is used by the rolling stock components. And when a train is running or when its locomotive is running, that time you have a lot of current in the catenary going through, that is used by the locomotive or the train itself, and then it goes onto the rails before either it is captured by the written conductor, or along the rails and along the earth it reaches back to the substation from where the catenary is being fed. So we can see that we have high voltage wire running parallel to the track, along the track. So that will generate a lot of static electric field, and that can get coupled with other devices depending on the capacitive coupling between these two things. Also, because you have an alternating current running in the catenary wire, so you have a very high magnetic electromagnetic environment. So magnetic fields generated in that area along the track, and that can also get coupled by uh, inductive manner to other devices. So these and third things, as I discussed earlier, other than the electric field and the magnetic field, which is visible, is the harmonics of power frequency being generated by a lot of switching devices used in propulsion systems these days. So this is the kind of environment in which train detection systems or onboard ATP systems they operate in, and there has to be some mechanism of ensuring that the immunity levels of these signaling devices is higher than the emissions on those specific frequencies from the rolling stock components. We will see a lot of standard references here, because you cannot control these things without having a laid down process and the immunity and emission levels and testing mechanisms in place. So EN 50121, this is the generic standard for EMC in railway environment, and it has five parts actually, and the most important part for SNT components is part 4, which describes the testing for identifying the emission and immunity levels of the signaling and telecom apparatus. You also can see part 3.1 and 3.2 for testing the rolling stock, how they need to be tested to identify their emissions and susceptibility. Wow. So here, again, as I said, a lot of references of standards, because this is the only way of managing EMC in the given environment. So if you look at 1214, which prescribes the emission and immunity of signaling and telecom apparatus, and how to actually test these systems for various elements. So the testing standards for SNT apparatus is described in standard 61000-4. And you can see this 2, 3, 4, 5, 6, and all these standards. They how do you test for electrostatic discharge? How do you test for radio frequency immunity? How do you test for electrical fast transient or burst immunity or surge immunity? And power frequency, magnetic field immunity, and then generic immunity for industrial environment. So this if all these specified tests in these are done on signaling components, then you know that its immunity and susceptibility level. And there are also limits defined in these standards for each of these tests, and that's how you get the compliance or certification. So we bring any signaling electrical or electronic component in the railway domain, then it has to be certified for 121-4. When we say certified, that means it has undergone all these tests and it has complied with the limits described there in the mechanism of testing. It is described there. So as a single engineer, we must be clear that this certain equipment has actually been certified against this standard, and that takes a lot of burden from us. We don't have to do this individual testing. There are certified test labs available for doing these tests and certifying the equipment. And EN 50121 generally has specified the immunity requirements for apparatus, and these requirements are actually given on port by port basis, and they've described these 5 ports, so to say, on the apparatus, the enclosure port itself, or the body of enclosure in which all the components are there, and then IO port, power port, earth port. So all these ports, they are defined to be tested. And for example, if you see this table 2, immunity of IO port. So in this, which characteristics the test responds to, what is the test specification, the standard, and the test setup specified in which standard, what are the notes applicable, and then what are the performance criteria and things. So for each of the ports, these tests and these tables are enumerated in 50121. This is just an example of IO port testing. So 121 was generic in nature. It was not for specific components. It was for every electrical electronic component which has to operate, has to be tested against 50121-4 with the specified test, and it should meet those limits and levels required there against each of those tests. We come to another subject now, this specific compatibility between rolling stock and train detection, and this is dealt separately with a specific standard because this is such a critical thing. And train detection, the fail-safe working of train detection system is the whole basis of any interlocking and safety in train operation. So that's why this is dealt in a separate set of documents or standards. EN 50238, I've just written IC because IC also, there is a both EN and IC standards on this subject, they are dealt by same committee. So because EN generally means European in nature, whereas IEC is much more international. So, but the content in both these specifications is absolutely word by word same. Okay. Is there any shadow coming, sir? Ramana sir? Or it is clear?
No, it's very clear. It's very clear. Akhilesh. No shadow. Yeah.
Okay. So this tries to 50238. What it tries to is it tries to define and specify the level of interference permitted by trend detection systems. And how it does it, there are test specifications for the track circuits, for axle counters, in which they have listed what tests to be carried out, and they have identified the susceptibility limits of all these components, axle counters and track circuits, especially those working in European railways. And based on that, their susceptibility limits are defined. And then those limits are shared with the rolling stock people to respect those limits in a manner that any interferences coming out from the rolling stock should never breach those limits defined for trend detection systems. Interference in trend detection can come from rail currents, from electromagnetic fields, which we have seen earlier, and the differential voltage between axles. Because when there is a current in the rail and you have two axles separated along the track, there could be a differential voltage between those axles. We'll see one example in one of the slides later. Right side, if you see the same information of electromagnetic interference and its sources is given in a pictorial format. So you have rail currents, and then you have electromagnetic fields, and you have wheel detector, track circuit, any other components on the track, and they are influenced by these rail currents and electromagnetic fields. So the compatibility will mean defining the boundary between the two in terms of emissions from the rolling stock should never go beyond the susceptibility of these devices. So the limits for the susceptibility of these devices are defined, and rolling stock then needs to be tested to ensure that it doesn't emit the rail currents and electromagnetic fields, which can influence these devices. Yeah, so this is the methodology of 5238. It shall be demonstrated that the rolling stock characteristics for generated and propagated interference comply with the trend detection system. Gabarit, this is another term they use for maximum permissible value of interference signal under defined operating conditions, including degraded modes. The information flow may be in either direction depending on which system is being changed. So if there is a new trend detection system coming, then it must respect the Gabarit again. That means it doesn't get influenced by the defined levels of interference energy. The one term which is being used very frequently here is the transfer function. It is the ratio of the voltage or current at the port or signal port of the trend detection element and the actual interference current coming from rolling stock. So the ratio between, so if say 1 ampere current from rolling stock is coming, and on the track circuit receiver port, the current level is say 100 milliamps. So you can say the transfer function is 100 milliamps by 1 ampere. So this is the ratio. On the right side, the same thing is given. So you have trend detection system. what is the sensitivity of the component, the transfer function, also include a factor of safety, and then generate a Geberit or maximum permissible value of interference signal that should not be broken or crossed by the rolling stock. On the right side, you have the substation and rolling stock analysis for generating those interferences, and then you compare them. If they are aligned, everything is good. Yeah. So this is one example which is described, and if you see, there is a voltage between two axles of a rolling stock, and how that can get transported to a track circuit receiver because of the cross bonding and another axle of one train on the different track being there. So this voltage actually coming from here and then going on to this, and from here it is going on to this. So the voltage on the track circuit receiver, for example, in this case, it is shown as alpha V, whereas the voltage between two axles was V. So alpha is the transfer function here. So how much of this voltage between two axle has been transferred to the track circuit receiver? This is second example, which is discussed in the standard, and is radiated interference. So you have a track circuit receiver within the magnetic field generated by rolling stock, and how that energy can couple with the receiver and cause it to malfunction. Now this 50238 has three parts actually. One is the general part, where it describes the overall methodology of ensuring this compatibility, and then there is second part, -2, which is about the track circuit immunity levels. And so what it has done is actually in this 50238-2, it has listed the sensitivity levels of all track circuits. For example, if you see on the right side, this is a table for UM71 track circuit, and at different center frequencies where it uses for different types of receivers, and what is the bandwidth to be taken at that frequency, and I naught is the current which is coming from the rolling stock, and it should not be beyond the given limit. And if it is more than the given limit, it should not be for more than the given time, or the maximum time during which interference current may exceed the. So if you look at the first line of this table on the right, UM71, it's working at 1700 frequency with a. So if a current coming from rolling stock of 0.3 amps within the bandwidth of 90 hertz, then it is okay. If the current is more than 0.3 amps, then it should not be for more than 0.3 millisecond. So that means if the current coming from rolling stock is 0.4 milliamps, then that particular current should not exceed for more than 0.3 milliseconds or 0.3 seconds. But if it is less than 0.3 amps, then there is no issue with the timing. That means it is anyway lower than the susceptibility of that specific receiver of the track circuit. So this similar tables exist for most of other track circuit equipment in this standard, and this these tables actually have come from testing of these equipments and those test specifications for the track circuits, how it should be tested, with what kind of filters and what kind of probes. All this is described in a different standard. I will come across. We will come across in some of the next slides. So this is the mechanism. We have limits specified for the interference for the trend detection devices, and those limits should be respected by the interferences being generated from rolling stock. Yeah, so this is a mistake here. Approach to RS compatibility with track circuits. It is 50617, not 717. Sorry. So this is the standard which describes and analyzes the track circuit and how to ensure that they are compatible with rolling stock. So for example, if you see in this right side diagram, so track circuit susceptibility limits, they are tested. For example, in the previous section, we saw 0.3 amps current. So this is the susceptibility threshold for the signaling component. Then you give an allowance for degradation or faults in infrastructure where there is a sudden increase in currents because of some faults in the system. And then that means this dotted line is the degraded susceptibility of track circuit components. Then you give a safety margin, and then this is the limit which should not be broken or passed or crossed by emissions from influencing unit, which most of the time it is the rolling stock or the rail currents. I think we discussed in one of this previous slides a term called Gabbard, and that was maximum allowed interference at different frequency levels. So if you test all the track circuit systems, Alstom track circuit, UM71, Bombardier track circuit, and all sort of things which are available, you will know their susceptibility limits at different frequencies. And if you plot that, that is what is described in the standard as overall Gabbard for trend detection systems. So again, this is very specific to European railways, where they use those kind of track circuits for which this is specified. In our case, we use some of those as well, and we in fact might be using some different trend detection or track circuit systems as well. So we need to do that actually, the testing of these track circuit components to identify their limits, and then we can have our own overall Gabbard. That means interference level plotted against the frequency in use. So this is the mechanism by which the compatibility between track circuits and rolling stock systems is ensured. And this is the emission limits based on that Gabbard. The emission limits for rolling stock are defined at various frequencies. So these two graphs actually are complementary. And this is, both of them are in the same Select standard 50617. which defines compatibility with track circuit. And coming to axle counter susceptibility limits, and how to ensure that it is compatible with the rolling stock being used or going to be used on that metro or railway. This is a table, if you see on the right side, from 50238, which has all the axle counting sensors listed on the first column, all sort of systems from various make listed there, which actually are working on European Railway. And then their center frequency and their filter curve, and then the magnetic field in X, Y, and Z directions for each of the sensors, the limits of magnetic field, which should not be crossed by external influencing component or device. And also the rail current in that specified frequency is also given, which should not go beyond that limit. So, and this table is based on testing methodology specified in 50617-2. And if you see on the top, it says rolling stock emission limit, this table. That means the rolling stock emissions should never go beyond these limits, which are specified here. So if you're using, for example, if you're using RSR 180 sensor, then these are limits for magnetic field and rail currents, which should not be broken or crossed by the rolling stock components, to ensure that RSR 180 never fails or never goes into compatibility issues with the train. Right. So, and then rolling stock, how it should be tested, that is specified in 50592. Unfortunately, all this is so standard driven, and they have tested many components and their susceptibility limits have been defined. And to ensure compatibility, what you need to do is to test now the rolling stock and ensure that the emissions from the rolling stock are not going beyond those defined limits. So this is the mechanism for electromagnetic compatibility. And this process, more or less, I see in all the metro systems is being followed. Even in DFCC, there are some specific requirements and testing on this front. So I believe even there they'll be ensuring these limits. And this is how we have to ensure for other axle counters which are not listed here, or other track circuits which are not listed in 238-2. So if we are using, for example, different axle counting systems than listed here, it should get tested first of all as per 50617 in certified lab, to define its susceptibility limits along with the margins, safety margins. And then we have an overall table of all the train detection systems we are using over Indian Railways. And then this table can become the basis for proving the compatibility with any new rolling stock which is being introduced. Rolling stock, when I say that, what I mean is the rolling stock which has this propulsion system on board. When I say new rolling stock, we believe that existing rolling stock is complying because it has been working historically for so long, and we haven't come across the interference or compatibility issues, or so I believe. Good. So that brings me to the end of this discussion. Final thoughts. We have a lot of scattered information around. There's some information incomplete if you look at the standards like this interference tables limit which are defined in 238. We don't have those for some of the local components which we have on inner railways. So we need to complete that, and we bring all this information into one document instead of looking at IR SOD, IR SEM, and this EN 50238. We can have references in that document for some of these things, but we should have one document which has compiled all this information. And I have seen this document with various other railways, Network Rail UK and Australian Railways, and I've seen that document available for rolling stock and train detection compatibility, not just EMC, but overall physical, for the braking, for all those things. This is available at one place, where in our case, the information is, and sometimes it is incomplete, and sometimes it is not available in one place in clear form. So I think there is a need for one of this document which has all this information in one place.
Yeah. So, Akhilesh, yeah, able to hear me? Akhilesh, so I request the participants, you can raise your queries already, which have been, what have been raised, those queries have been compiled. And then Akhilesh, I will cease the presentation and then I'll post this screen to you, and then it's easy.
So, right, I will stop
You stop the
sharing.
presentation. Yeah, yeah, please, yeah. So these are the queries which we have been raised at the time of registering the application. So I think it is visible. Yeah.
Yeah.
Yeah. So just quickly go
Please
through them.
share the actual challenges encountered during TPWS and TCAS commissioning.
So maybe some questions may be asymptotic and it'll be, I mean, quite away from your this thing.
Yeah,
But
but
this
I
is
can
what
say,
people are expecting, actually expected this thing.
okay,
Yeah. Yeah.
since TPWS I was associated significant time, so I can say uh, the issues were related to rolling stock were that there was space for putting the onboard computer was not available, and it was available only in some locomotives, but not in all. And in most of the cases, you will have to displace or move some components, some rolling stock components from one place to another to create a space for onboard equipment. The key interfaces with the brake and odometry, they were having a lot of issues. And most importantly, I think the training of the driver, that was an issue, because suddenly you have put a screen in front of him. He was driving, looking at signals and on the track around, and suddenly there is another thing to look at. If he doesn't kind of respect the limit specified, speed limit specified in the TPWS DMI, then the brake will apply. So these kind of things were coming up, and this human factors consideration I think this was something overlooked. We did later on, I think, did a lot of training, and over a period of time, the drivers, the loco pilots, they became used to the system. And then I think in later period, around 2012-13, this was liked by them because they were getting information in advance, and the number of unwanted breakings came down. So this was something learning. So I'll say brake interface based on the locomotive and the driver training.
Just to add, hello.
Sir,
Sir.
Just to add to what Akhilesh just now mentioned, there is also a very strong standardization of the wiring protocol on the locomotive, which is important from the angle of being fire resistant and also slightly less prone to the EMIs within the system. That is one area. And the second issue is about the mounting of the tacho generator, which is required from the angle of spare axle to be made available for that purpose. Thank you.
Yeah.
thank you, sir. Thank you.
We'll go to further this one, smart coach with the use of AI and IIoT.
I don't know, but AI and IoT, they will not influence compatibility for sure. So
Okay.
with the topic of discussion, I think it doesn't relate completely.
Yeah. So the compatibility between the speed of trains and signaling. So
Yes, this is a very important requirement. You see that different speed, the braking distances of trains will be different. And if you have designed your signaling for a braking distance of 1 kilometer, so you cannot run a train at the speed at which its braking distance will be more than 1 kilometer. So that's how the braking distance, speed of the trains, and the intersignal distances, they are all I think interrelated.
yeah. Okay. The interfacing methods for existing signaling locomotives. So must be
Existing signaling locomotives, interfacing mechanism. Yeah, so if you look at ETCS level 1 or any other ATP where you pick up information from bellies, you have a BTM, an onboard computer integrated on the locomotive itself. In ETCS level 2, maybe it is the interfacing is through radio, similarly with the Cbtc system. So these are all, I think, now very much well defined, and it's available in some document or others. So there are mechanisms and systems available for interfacing. It depends on what system you're talking about.
Yeah. So someone is interested in AI and ML use in rolling stocks.
Unfortunately, I can't comment on that.
AI.
Yeah, artificial intelligence and machine language. I don't know if they will ever be used in propulsion, because propulsion has to be very well defined. You can't leave it to machine to accelerate and brake based on its learning in the past. But it might be useful in diagnostics and those kind of systems, maybe, to identify and detect whether a component is going to fail. So maybe in that respect, it might be, but not in propulsion and things like that.
So regarding braking system relation with the signaling onboard systems. So
I think this is covered in detail in this presentation. This braking is the very basis of any signaling system.
So EMI, EMC also you talked about related measurements.
All the measurements, how it is done, they are specified in 50592 and 50617, and the limits are defined in 50238. So that's how it is. So this discussion, sir, I believe can serve as a pointer to the right direction, instead of because this is such a wide subject, EMI, EMC, you cannot cover. Even for one specific train deduction system itself will take multiple sessions. But I think people will come to know that these are the documents where they can look for deeper information and
Yeah.
that way.
Yes. Yeah. It is definitely helpful. Yeah. Then basically determining product specification for interface elements such as relays.
Relays specifications are very detailed, available with RDSO, I think, and they have served the purpose for last so many decades. So I don't think there is any change or anything is needed there.
Yeah. So the next question is Indian Railways planning to install ETCS level 2 signaling. What modifications need to be done in locomotives and other rolling stock?
As I said, we have to make a space for onboard equipment. Uh, Generally, it's a rack of almost what you could say around 700 width, length, and depth, and maybe 1.5 meter high. So this kind of a space for the main computer, and then you need space for DMI, and it has to be placed not where space is available. DMI has to be placed considering the human factors, considering the field of vision of the driver, so that he's able to see DMI at the same time when he's looking at outside environment in which you're operating the train. So these are the factors which has to be considered while installing onboard equipment. And yeah, I mean you install a lot of odometry systems, interface with the braking. That is the most challenging part. In fact, you have to put a lot of electromagnetic on solenoided valves on the brake pipes and the main reservoirs, and that is where, because that is a safety system of the rolling stock, and when you interface there, it has to be done in a very defined and approved manner, where both the subsystem owners, they come and discuss and design that interface.
Yeah, even the BTM antennas also has to be mounted below this thing.
Yeah,
Yeah, this one.
I think that is the easiest part.
How difficult and challenging will it be to implement CBTC on main railways? So of course, it is very
CBTC,
yeah.
CB, I think train integrity is something which is still missing. So
Yeah.
moving block is still some distance away on line.
Yeah.
ETCS level 2 is the best we can aspire for in given moment or given scenario.
Yeah. So how is he is a railway veteran, looking forward to hearing his experience as an example for better understanding. Of course, this is the opinion is given by this thing is not
Yeah,
really a question. And then RS-STC interface. I don't know what is the STC.
this is rolling stock signaling telecommunication interface, I think,
Interface.
and that
Okay.
is what we have discussed
That he
in
wants to.
this.
Yeah, is expected from this presentation. I think it has been discussed here. International standards and standards adopted for the Indian Railways related to signaling, of course. Uh, and neutral section detection and how to improve it functioning through signaling. Yeah, so it must be.
Yeah, I can maybe say that we have this system in place in UK Railways, where you have APC magnet, or automatic power control magnet, placed just before the neutral sections. And when a train passes over, it is just a magnet. When train passes over, it picks up this information, and then it switches off or disconnects the current coming from the panto, or the circuit breaker. And immediately after the neutral section, there is another magnet which tells it now you're beyond that. So the system then connects it automatically. So there's nothing to do with signaling here. This is a separate. There is a control device for switching those circuit breakers with the quaternary current circuit breakers coming from panto, and that is activated by these track magnets placed along the track near neutral section. So
Yeah. So then the home signal, distance signals, inner distance signals, shunt signals. Why all this needed? How these details should be known to civil engineers. What are the critical areas at different situations? So,
very, very wide question. I think this is about the whole purpose of signaling. There's a distance, as they discussed, I mean, signals are to indicate the movement authority, whether the train is allowed to proceed, and if allowed to proceed, where it will need to stop. So aspects tell this kind of information, and the driver route learning and the operations learning is enough to give him this understanding, and that's how this works.
yeah. And somebody wants to know that this compatibility of present signaling and rolling stock in high speed scenario. What is the latest
Yeah,
in this
so
area? How IIoT can help in this area? Yeah.
compatibility of signaling or with any rolling stock, the methodology is going to be the same to test the signaling equipment and identify its susceptibility and define that limit, and then rolling stock emissions are tested so that they don't cross that limit. This is the methodology. Whether high speed or low speed, it is the same. Some of the speed dependent things will change, of course. Your braking distances will be higher.
Can trolley suppression be achieved by installing one more sensor in advance of DP?
This is again, I mean, trolley suppression is anyway there on the most of the axle counters which are on Indian Railways. So why we want to achieve it with another DP?
Okay, GOA4 technology in India.
This is again this metro automation terminology. GO4 means unattended train operation, where you don't have any train attendant or driver, and it is defined in one of those, I think, Cbtc standards. So generally, you have 3-4 actions for starting the train, stopping the train, and door closer, and managing the emergency situations. In case of grade operation 4, all these 4 are automatic, and that is where the challenge lies. So, but in Delhi Metro, I think line 7 and line 8 both are supposed to be GO4, but they're still working with driver, and over a period of time, I think they go into unattended.
Yeah. So then the new inventions in the field of signaling in the world, of course, this is a very open expectation.
This we can have 2-3 sessions on that.
So this is the during the session. So some of the questions have been raised by the participants. Kindly, Arun Saxena sir.
Yeah, this 13-meter log bar, I think rightly pointed out by Saxena sir. This the maximum wheelbase that I think that is related with that. So thank you for that, sir. Unfortunately, when I joined railways, these lock bars were going out, and I didn't see many. So,
so Waris is saying that in the slide 12, slide 12, the spacing of the wheel is in marginal value from calculation on 200 kmph. Does this mean that for higher speed, say 300 kmph, the para of IR SOD to be revised, or the axle counters for high speeds are different? The spacing of
so you have to identify actually that 25.9 millisecond limit of interaxle distance is the worst case for one worst kind of sensor among all those available on Europe. We have to see in our case what is our worst case, and then define the limit. I have calculated, for an example, at 200 kmph. We are running trains at much less than that at this moment. And whenever even 200 kmph, you have so up to 250 kmph. I think that distance is all right. That interaxle distance, and that also I think for some specific rolling stock. Otherwise, for passenger rolling stock, it is much higher. So you don't have to change the specification or anything. You have to assess what rolling stock you will run at that speed, and what axle counters are there, and what is their response times, and whether these two parameters will match. So whole idea for this bringing on this presentation was to trigger this thinking that there's something like this we have to look from a signaling perspective.
The question from Arun Saxena Saab, that automatic brake test tried on onboard ATP systems could be a more realistic a deceleration constant assessment and thereby braking distances. So, sir.
Yeah.
Sir.
Sir, you like to answer yourself?
Then this is actually for TKD, this was a very important feature which was able to detect under the actual realistic situation what could be the braking distance of a typical rolling stock with different combinations. So this particular concept, I think, has not been used by other foreign railways. This, I think, feature should be used, in my opinion.
Yes, probably so. But all these data-driven systems, they need a guaranteed limit beyond which calculations should not go. So, because
why I was mentioning this was because you are trying to refer to certain tables, which are also approximations. And if you remember, when we did the ETCS level 1, TPWS, we were having a hit and trial method.
That's true, sir. And that's why it took some time initially to actually bring the braking curve, actual braking curve of the trains in line with the signaling system available on track there. And but what I mean to say is that automatic brake test, when you say that, means it is a computer calculation, and that calculation, what is the guarantee that it will not go wrong? So we have to anyway define a limit that if computer says more than this, it should not be accepted. So we have to have a worst case braking defined, whatever it can be, but it has to be there for each of the rolling stock.
Good afternoon, Akhilesh. Ramesh here.
Sir, namaskar.
I think this automatic. Namaskar. How are you?
I'm good, sir. How are you?
I'm fine too. Saxena, this automatic brake test was a factor that came up. You remember that I was doing the PPW's earlier versions in the Chennai and Delhi one. This was a requirement which came up with ACD. Somehow there they had gone around and put a fact that the train would start and it'll run the first kilometer and it'll check its own braking and then load the braking parameter inside. So this was demanded on the ETCS, and ETCS rightfully said, no, we don't do it. So what Akhilesh says is right. There are far too many parameters to come to one deceleration point. Far too many. And the type of rail and wheel that we seem to be having here and what's used abroad, I don't know, the chemical composition could be the same. The slip and slide readings that came out of France or Italy and what came in India were totally different, and we could not generalize it. So I think this we'll have to work on it, and it will take some time. But automatic braking distance calculation is a little ambitious, and I don't think we should get into it now. The doubt over, doubt under will be there. That's the element of safety.
Yeah. At the same time, I think TCAS is designed with this functionality, which Arun sir is saying, and maybe that experience coming out of that those projects using TCAS will tell more story about the use of this function in days to come.
At best, like you can combine both the words and take one parameter. I mean, take one whatever deceleration parameter, gamma or alpha, whatever it is, and over a period of 20 or 30 kilometer run, it keeps repeating itself, depending on the number of breakings. It depends on the weather, it depends on the load, it depends on the brake pressure that's there on the train, so many other factors. So yeah, I think if we can get to this, it would be a good factor. Anyway, it's something that we can keep in mind.
Yeah. Yeah, sir. Sir, Padke Saab actually expected that TPWS and TCOS will be part in this presentation. So,
I'll respond.
yeah.
So,
So,
Saab, we'll
sir,
have a session on TCAS very soon.
very soon, sir.
We are going to conduct.
Yeah. And then, sir, Rajendra Jain sir wants to know whether the presentation be mailed or made available on the IRISET website. Sir, as a host, IRISET, so actually, if a speaker wants to spare his presentations, definitely I'll mail to each and one of them who have been registered with the sessions. But if speaker doesn't want to spare his slides, I am helpless. So I can't, I mean, do that, sir. So now I think it is Akhilesh, you can react.
No problem, sir. I can give it to you.
Okay.
Maybe you can use it with specific people instead of putting on web for free for everyone.
Yeah, no, only those people who have been registered with this only will be
Yeah.
sent to them. That too, I asked a question that whether they require the presentation or not. So most of them, they asked the presentation copy. Yeah. Okay. And then, sir, we'll go further. This thing, please consider and clarify on this question from the Rajshekaran. Miscounting taking place during shunting, midway reversal. And 3 questions he raised. Disturbance to axle counters during trolley and lorry on rails, and reliability of axle counter working during the EMI, wide its measurements, etc. Something.
I think this EMI part I have covered in my presentation. Disturbance to axle counters during trolley. So as I said, the axle counter sensors, they work on detecting specified wheels, not anything on everything. And then also to suppress if suppression is required by a specified manner. If you bring anything beyond the limits in terms of wheel diameter, flange dimensions of height and width, then the response of axle counter is undefined. And that is the problem most of the times. The kind of trolleys and lorries being used, their wheel dimensions may neither comply with the schedule of dimensions or the specified trolley dimensions from RDSO, which need to be suppressed. So if you bring anything else, it can create issues on axle counter. Miscounting taking place during shunting, I'm not sure about this midway reversal. I'll have to.
Good afternoon, sir. Sir, it is during shunting, the wheels are being reversed without fully crossing the transducers.
Yeah.
Since now we are using the axle counters in yards in a major way, this is becoming a nuisance actually. Every time it requires resetting all these things.
So you have to, Sakran, I think you answered yourself that if wheel is there midway on the sensor and comes back, how do you, expect that system to counter reject it? What overall it knows is that part of me got affected by something. I don't know what has happened, and as a fail-safe reaction, it might go into error. So
Akhilesh.
that's the whole point.
Yes, sir.
Akhilesh, especially during shunting operations, we have a concept of counting head control. And that counting head control strategy could be, I think, has not been deployed on Indian Railways. That could be a way out of this shunting problem.
That is there, but it also relates with actually the operation you're being planned. Why we should have a sensor placed at a place where shunting operation will necessitate a train wheel to stand on the sensor. You place it further away. It all depends on the operational planning as well. It is not as simple as placing a sensor and then detecting each and everything, whether you come halfway, whether you go full way. So the technology has its limitation, Rajasekharan. So, but I think I can take this discussion separately with you because it is not so straightforward to answer just like that. I can explain you in detailed manner in a separate maybe discussion with you on one-on-one.
Thank you, sir.
Sir, one more question from Arun Saxena, sir, that interference generated by power electronics and AC coaches also is an area of concern.
Yes, sir. This will become more and more as some of these uh, active devices, solid state active devices, they generally they have the chopping frequency in kilohertz and things like that. So the emissions from that, they are in kilohertz and that harmonics of those kilohertz. So if if the if the energy being chopped by those electronics is sufficient, it might actually generate enough interference to for the track circuits and axis counter kind of devices. So even that is part of study. You're right.
Okay. So, sir, DG sir, SK Goel is asking you a question. Onboard electronics used for the loco controls, do they have different standards for immunity?
Sir, for the EMC 50121 has 5 parts. In fact, in this 3-1 and 3-2, they talk about rolling stock testing, and there is another standard. Just to, already so many has been mentioned. 50155. This is for the electronics on the rolling stock, specifically whatever you asked. So 50155 is another standard which can be looked into if you're looking at rolling stock electronics part and its immunity and emissions.
The KV Reddy is Senior Professor Signal is asking that once the product is approved and installed, is there any requirement to check these values periodically during its lifetime?
I will say no. It is mostly at the initial phase when the systems are being introduced, when you have to ensure this compatibility, because if it is being used for so long, then that means they are compatible. But if you start getting some issues, recurring issues, then I think there might be a need to look at this issue again.
So one more question supplement to this, Yadavji.
बताएं sir.
Announce
One thing is that due to aging, is there any possibility of equipment not able to meet the EMC requirement at a later date? That is basically the thing which we want to know.
So, the way electronic components degrade, that possibility is not there, that its susceptibility or its emissions will increase. So I don't think there is any concern on that front, that over a period of time they will become more susceptible or they will emit more energy than what has been tested already. But as I said, in during operation, if we are getting some repeated kind of issues, then that specific case might have to be looked from EMC perspective as well.
Thank you.
Thank you. Kindly mute your microphone, please. Thank you. So, what will be the impact of EMC on board equipment loco operations?
He is already answered.
You already answered that one. So, then the 50121-4 for signaling is stated. What is the standard for rolling?
I think he has answered it. Venkat has answered it. But just give me a minute. This is my sharing, and I think I would need the attention of Yadav and maybe Arun Saxena. Sir, when you started talking about the wiring requirements in a locomotive, what we practically saw was we were using double screen cables from the TACO to the EVC. One fundamental mistake that Indian engineers did, and we still are doing it, is we believe that we have to earth both ends of the screening. This is not to be done because then you're creating a ground loop. This was pointed out to us rather rudely by the French people. So we had to remove one end of the screening, both in the locomotive as well as on the track side. Supplementary to this, Yadav, there are a lot of discussions now going around on various EN standards. We are a later entrant to a locomotive. Now we can't go around and ask them to do something for us. So can we make cages, EMI cages, suppression at source, where we put our equipment inside, and we are immune from outside, and our equipment does not radiate anything to impact outside. So can we look at something like a Faraday cage or something? This I'm talking about the locomotive. I'm also going to talk about this for our location boxes on the track side. So more and more electronics are coming into it. So I think RDSO can go with this. And plus, right now, I think RDSO may have done it. I'm not sure. We will have to clearly have a sign off with the rolling stock manufacturers, Indian Railways, all our RCF and all these people, that earmark space should be provided for future signaling equipment. And we had a lot of problems. WAP5, the space was given, but when we went and saw it at the site, they were different for every locomotive. Second, the control cables that were running to the traction motors, the idea was all the control cables, electrical control cables would be on one side. Our data cables will be on the other side in the undercarriage. That was also not respected. And third, there is a requirement that the BTM and the BTM antenna has to be in the shortest distance possible. Many times we found that we had to position the BTM in between the two bogies. The length of the cable was crossing the recommended distance. It was leading to pickup of interferences. Much of the ETCS level 1 problems initially on southern as well as northern was basically because of EMI EMC references. A lot of things can be done. Standardization is required here. I still pitch for some sort of a cage, an EMI cage, which can be put inside your OBC equipment, can be housed inside it. It can be kept anywhere in the locomotive, and the locomotive can create whatever interference it wants. We can create whatever it wants inside. We suppress it at the source.
Right,
we start looking at something like just a suggestion.
Okay. Sir.
And work installation process for termination of cables, screen cables, asking for a powered axle and a non-powered axle for TACO purpose. These are points I think we'll have to sit down and have a sign off with the rolling stock
equipment on.
Yeah.
So this is what I want to do.
Okay, sir. So that is your last one, sir. The emission limit.
That's it.
Yeah. Okay.
Ramana, if you permit me, I just want to ask one question.
Please, sir.
Chopra,
sir, please.
Mr. Akhilesh, just I wanted to know, since we have worked on the locomotive, this TCAS is also coming and ETCS both are coming.
Sir.
Will it be possible for fixing both the equipment on the same locomotive?
Sir, I was finding it difficult to place one. And but if there is a will, there could be a way. We'll have to displace a lot of onboard equipments because then you will probably have two DMIs and two set of odometry, two set of Belize transmission.
Or and brake system can be common. The other things can be there, because why I'm concerned is that the South Central Railway has gone for TCAS and we are going for the ETCS. If we expand both the sections, then a locomotive fixed the TCAS cannot go to ETCS or vice versa. We will have a serious operational problems. So this my take is only that unless we make arrangements that both the systems can be provided on the locomotive, we'll have problem.
So I think the way forward will be to make them compatible. That means the track side information being relayed should be able to be received and decoded by both of them in a similar manner to extract the information. For that, you can have two set of radios. Onboard computer, you don't have to have two. You can have different radios and maybe additional protocol or software to convert the information coming from different either ETCS or TCAS wayside component, convert that into the data, which can then be processed by the same vital computer.
I fully agree there. that it could be a common vital computer and even the common DMI. Even a common DMI could be there. So that depending on the inputs available at any point of time, whether it is TCAS inputs or the ETCS inputs, you are able to have a system which is interoperable and workable.
Right, sir.
Yeah, I think this is an interesting.
Have to be done on this.
Sir, just
I think this is an interesting submission, sir. Submission has to be taken forward in a very, very right way, because TCAS, you can actually sort of look at TCAS as a degraded version of ETCS level 2. And therefore, you can have something like a switching ballast just before he enters the TCAS territory. And as Yadav says, the switching ballast now gets the OBC ready for a degraded ETCS level 2. Now, let us reconfigure TCAS, come down to an RBC, again a degraded RBC. Let's come down to a degraded RBC. Maybe we can use the same radio. Maybe we'll need, I don't know, this RBC is a real fantastic thing for the track. It reduces the cost. It doesn't need to give a 128-bit telegram for an ETCS level 2. So something there, we can do it. It means that both have to sort of sit down together and come to a common spec. Degraded ETCS level 2 should become TCAS.
Basically, sir, if you see the European railways, sir, if you see the European railways, even though they adopted the ETCS system, but still they are having on their locos their national systems also. So every country they had their own automatic train protection. So if you see, sir, this kind of arrangement is available. So whenever they run the train in their country, if the ETCS is not ready, they will go with their national train protection system, and then whenever they cross, enter into the ETCS territory, it will. So they will have a two kind of a sets. To read the information from the ballasts. So that is already existing in the European railways. So the TCAS and then ETCS going together, it should not be a problem, sir. So we should have a two set of equipment. And
but the conscious decision has to be taken towards.
Yeah, of course.
Sir, I'll just add on to this what Venkat Ramana has said. The whole problem or the whole premise on which ETCS was developed was that because there were so many countries having their own train protections, and one train running into multiple national boundaries had to have 7 to 10 onboard systems.
Yes.
And that is why ETCS was developed, to have a common signaling language. And what you said that it is also having national, that is only a temporary phase when ETCS is being deployed. Finally, that will go away. Finally, what will be there is only ETCS, nothing else.
Yeah, of course. Yeah. So from the participants, any more questions? And there are many.
I saw Goel sir raising his hand. So
So it's.
I just want to pitch in there. This subject is being hotly debated. Interoperability of level 2 and TCAS, and we have scheduled a session on that. Please be on standby. There will be an announcement.
Yes, sir.
We'll focus on the issue of interoperability between.
Yes, sir. We'll have a separate session, sir, on that. Sir, there are the many officers from the various departments, from the mechanical and electrical. If they want to share their thoughts or anything, they are welcome. So CMPE Diesel, South Central Railway is available. CLE, South Central Railway is available. And the IRMI faculty is also available. Sir, IRMI as well as ERI also is there, sir. So please come up, sir. Your comments, because the first attempt we made to have a cross-platform lecture like this, signaling and carriage and rolling stock. So a concern of all the three departments. AE Lalaguda, AE ELS Lalaguda. So there are many people are there. CLE, CMPE, and ELS, and there's a diesel local shed. Yeah, please. I think somebody wants to. You can unmute your mic and speak, sir. I think you have to unmute your mic and speak.
Yes, sir. Nice introducing that I am Vijay Kumar, CMP Diesel. I have gone through the presentation. My one more this thing is that now we are going to introduce already 19 locos are provided with the TCAS system, and they are playing in Secunderabad Wadi section.
Yeah, please go ahead.
Yeah, one point what we'd like to know is that if now the tracks is certified for a 130 kmph also in due course. So our locomotives are 120 kmph maximum, one particular stock WM3A locomotives. Next other one is a WDP4 which can go for 140 this one. So in this type of speed in the locomotive, our TCAS is actually functioning with respect to the signal what it is picking up from the control, that is from the relay system. Similarly, electric locomotives also will work like that. But my one question, with the varying speed of the locomotive and varying signal strength of that one, the train control system, how effective it is going to be, that I wanted to just know it.
Yeah, Yadav.
Our TCAS is more related with the TCAS project, I think.
I think Venkat
Yes,
can
yes,
answer
correct.
it.
It's absolutely.
Venkat can answer that.
Sir, as far as the speed is concerned, whatever is the speed, like if you say that your locos can run only at 120 kmph and signals can work for 200 kmph or different speeds, but ultimately whatever the loco speed is there, that is the speed. I mean, we are going to limit it. I mean, whatever the minimum speed, what is the among that, what is the maximum we can get? That is the only thing we are going to have that. I don't know, sir. I mean, able to answer completely.
TCAS can permit up to 160, not an issue.
Sir.
TCAS is an overlay on signaling design, I will say. So whatever underlying signaling design or braking distance is available, TCAS is just acting on that. So it is not a question of TCAS, it's question of the inter-signal spacing and the signaling design already available on the section. TCAS is just capturing this information and passing on to the locomotive to behave in a manner that acts as a safeguard for the in case driver forgets to control the train appropriately. That's the only thing it does. Otherwise, it is not introducing any new thing.
Yes, sir. Correct, sir.
Okay.
Sir, I have one more question. May I continue for one more question?
Yeah, please.
Because now electrical territory, electrical locomotives also there with this kind of anti-collision system or this one. Will it switch off OHE also? That kind of interconnecting interface is made.
So are you talking about APC, automatic power control?
Yes, sir. Automatic power control. Correct, sir.
So APC, I don't think it is deployed on Indian Railways anywhere. I'm not sure, but this is an example I quoted for that question of panto lowering and going back in neutral sections. So that system is, they install a magnet just before the neutral section and another one after the intersection. That is picked up by the locomotive and it switches off or kind of disconnects or breaks the circuit for the OHE current. And when it has gone to the beyond the neutral section, again, it gets the signal from the magnet that now you are beyond the neutral section and it again connects to the OHE section. So that's a very simple thing. It is independent of signaling. It has nothing to do with signaling. It has a small receiver under on the under frame of the locomotive, and there is a magnet on the track, and that's how the information is picked.
Sir, right. Thank you.
I can share you little more details on that.
Yes, yeah.
I'll send you specifically because you are having interest on that.
Yes. Okay.
Yeah.
Right, thank you, sir.
Any more questions? Participants? Yeah.
Good afternoon, sir.
This is CLE. Please speak up.
So good afternoon, CLE Thauriya, 1000 Radio, sir. Sir, locomotives, a lot of within cab, a lot of equipments are coming independently, like RTSA is coming, then this TICAS is separately is coming, and the loco RDS is separately is coming. A lot of activities driver has to be done. So because it has to be integrated and has to be designed as a sitting with all the departments, what are the connected, the signaling and rolling stock, and the operating department is bringing the RTAs. So all these activities, and there is no space available in the cab as well as even in locomotive also. What SAR is saying 0.7 into 0.7 into 1.5 meter. So very difficult to get in the WP7 because of HOG is added. After HOG attending in the one track, small motor, blower motor also difficult to, we are lifting the roof. So we have to be seen as a holistic approach, as integrated approach, and space has to be designed. There has to be the water cabling, suppose signaling cable from where to go, and what are the power cable where to has to go. Then has to be laid up. Cable harnessing has to be thought up and has to be made it in the initial stage of design of locomotives. Otherwise, it is coming on the way again, running the power cable over the control cable and interfacing of the EMIs. All these problems are coming. You know what people are saying that what are the keeping of the antenna. Antennas are 2-3 antennas are coming. Then sensing devices are coming 2-3. Approaching is very difficult. Cattle runners are taking place. So this a lot of this this underneath this what are the TPWS equipment is damaging, sir, because of it's not properly spacing, unable to access also. One TPWS item, this what is the underneath the item, difficult to attend our equipment. So that this all has to be seen in holistic approach, sir.
That's, I think, very rightly said. There has to be holistic approach for sure, and we also have to see what is necessary and what is not. So if we really want an onboard train protection system, we will have to have a space. We might let go of some other things which is not of that criticality, or we can move a few things. I found this. In fact, we surveyed all sort of electric locomotives, and we had, along with at the RDSO level, like electrical directors, a plan that if we have to put this system in this locomotives, what particular component existing in the electrical locomotive need to be shifted from this place to another place. This complete plan was available to make space for onboard system, because as a policy, if you've decided to have this additional safety layer of having ETCS or TPWS, then we have to have the space there, because it is only the onboard computer which stops the train or which regulates the train based on the information coming from track side. It cannot be done any other way. We have to have that space available there. But you're right in that manner that an integrated approach has to be there for all these systems, driver advisory systems, and all these systems which are emerging. There has to be an integrated approach for installation.
Yeah. Okay. Any more questions from the participants, please? Yeah, if no more questions are there, I request Mr. G.K. Dwivedi, Chief Safety Officer, Southeastern Railway, to summarize today's session. G.K. Dwivedi.
Good afternoon, sir. Am I audible?
Yeah, you are clear and audible.
Good afternoon, sir.
Visible also.
So first of all, let me thank DG Reset, Mr. Goel, you for hosting this web presentation on a very appropriate topic, which has generated a lot of interest. And first of all, it has broken the silos also, because everybody is interested. Electrical is interested, rolling stock people are interested. Even no civil engineer was there, but I think they might be also interested. So this is a very good initiative. And one very important line I have picked up from the Akhilesh version, that this presentation is nothing but a pointer in the right direction. We have to do a lot afterwards. It has pointed out in the right direction, and we have to think for the futuristic things as well as our existing things also, because in the process of introducing multiple systems over the Indian Railways, basically we have forgotten our counterparts. For example, very simple thing, while signing the joint safety certificates for the speed enhancement or for the introduction of the new locomotive or for the introduction of the new rolling stock, although the cases move through all the head of the departments, but what are the things required to be seen in that? This presentation has basically raised those issues, and it has basically opened our eyes to look for the existing system also as well as the future system also. Very good concept diagram what he have shown on the fouling mark, separation between the fouling mark and the track circuit boundaries. So these are the many small things which in the field our people are have to follow, and this information has to go down the line. So basically this presentation can be thought of for the interest to the existing system and coming system which are going to come forward. And the very important key takeaway from this presentation is that there is a need for a combined document which gives the information readily available pertaining to the locomotive, pertaining to the rolling stock, because we have gone for the HOG, where the power line is running from the one end, loco to the brake van. And similarly, in the rolling stock, also in LHB stocks, there is a lot of electronics. In AC coaches, there is a lot of power devices. So it is an appropriate time that we should go for this combined document, which other railways are having. With my experience for the British Network Rail, we see that there is a RSSB there, which go continuously up. New system comes, or any changes comes, or any issues comes. So there is a strong need for that, and I think with this takeaways, similarly for the lot of automatic signaling systems are also coming. There we are basically having a some sort of tailor-made design with 1 kilometer braking distance, double distance territory, and all these things. So there also, if we want to fine-tune the section capacity and relocate the signals spacing, then in that direction also we have to sensitize our signal design teams for all these issues. So with this, I would like to thank Akhilesh for touching a very relevant topic for the Indian Railways and for all our friends, whether they are from the rolling stock, from the locomotive. And I thank to the viewers also, because there are a lot of interesting questions that also come. So thanks to everybody.
Yeah. So thank you, Devedi. And our Goel Sab wants to wrap up the session with his words. Sir, please, sir.
Thanks a lot, Abhishek, Akhilesh.
Thank you, sir.
This is close to, we've done around 30 sessions ever since the lockdown was imposed. And yeah, like a father, each child, each baby is important, precious. But today's session, I would rate at one of the best we ever had.
Thank you, sir.
The subject pertains to multiple departments, and you have left the food everyone.
Yeah.
SNT engineers, loco engineers, for rolling in stock engineers, and for me, for a teacher like me, who has to train the signal engineers. We had close to 110 participants from various departments. I'd like to place my sincere thanks to each and every one, seniors, who find their time and make the session special with their inputs, and the youngsters are always willing to come out and join these sessions. Thank you once again. We'll keep you engaged in the days come as well. Please stand by for the next announcement. Thank you. Thanks a lot. Have a nice day.
Thank you, sir.
Thank you, Akhilesh, for your professional presentation. A very nice way. And there, if you see the chart, there are many compliments are coming for the excellent presentation. Thanks to a lot to everybody, and thanks a lot for a new paradigm move on the online interaction. Very interesting. So these are the comments who are coming. I'll capture them and then I'll send a file to you also. So I thank one and all the participants for the patient, hearing and also not disturbing the session as such. Thank you very much. So thank you very much, sir. With this permission, I'll sign off. And then, yeah.
Thank you, sir. Thank you.
Thank you. Thank you. Today's session, Akhilesh, on 104 people, 5 people have maximum touched at one point of time. Yeah. So mostly it's stable around 88, 90 people. Yeah.
That is good number, sir. And
yeah, that's a good number. In fact, we are expecting more. In fact, we handled up to 350 people also in particular session actually.
Okay.
Anyhow,
Okay.
so thank you. Thanks a lot. Yeah.
Good, sir. Thank you.
Good.